Hey guys, this is Mr. Barthold, and the purpose of this video is, as you can see, I have some objectives here. The biggest one is going to be to apply the law of conservation of momentum. That's really the point of this video. But to do that, we are going to have to be able to determine the total momentum of a system of objects. So those are the two main objectives for this little mini lesson here. We'll start with the first, which is calculating the momentum of a system. The basic idea, formally, the total momentum of a system is equal to the vector sum of each part. So we can, basically how it's typically written out, remember P is the symbol for momentum, so we're looking for the total momentum, little subscript, is equal to the momentum of the first one plus the momentum of the second one, etc. If you have 5 of them, you just add all 5. You add them together. So it's a pretty basic idea. The key word is the fact that it's a vector. Right? So it is not just the sum, but the vector sum. So it's going to, that implies that direction is important, right? So both direction and magnitude as a vector. So we're actually looking at the vector sum of all these. So we should add vector symbols above our variables P for momentum. So let's just do a few examples of applying this. Again, literally, it's just adding each. So suppose that we have two planes, 2 fighter jets, each with a mass of 12,000 kilograms, and they're escorting a passenger plane, which has a mass of 350,000 kilograms. I'll give you the speed of all the planes. They're all flying the same speed, 100 meters per second, and we're going to determine the momentum of the 3-plane system. So we have 3 individual planes, and we're going to treat them all as if they were one object or one system. So what is the momentum of the entire, all 3 of them together? This is just going to be the sum of them, right? So total. Excuse me, this says photo, let's erase that. So we have 1 plus 2 plus 3. So I did say that direction is important, and for this first example it says all 3 planes are flying east, so they're all flying the same direction. So we do just add them together. All the momenta are acting in the same direction. So momentum, as we know, is calculated by mass times velocity. And so we have 3 different ones that we need to take care of. 2 of them are the same, so perhaps we can say that we can combine 2 of them and then add the 3rd one. So we have 2 fighter jets, so 2 fighter jet momentums, right? So that momentum is 12,000 kilograms multiplied 100 meters per second. So this is 1 fighter jet times 2, and we're going to add to that the momentum of the passenger plane, which is mass times velocity of that, and the mass is 350,000 kilograms times also 100 meters per second. And so the total momentum would then be 2474 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7 kilograms meters per second. So this is the total momentum. I'm writing as best as I can. I have a stylus here. It's kind of got a not too fine of a tip, so pardon the bad handwriting. But just adding those together, you should find that they do, in fact, equal 3.74 times 10 to the 7th kilograms meters per second. All right, so looking at the, I guess, I won't say trickier, just exploiting, or looking at the vector sum, so taking these directions into consideration. So we have here, in the second example, a blue truck that is traveling east, and with a speed of 20 meters per second, and a small white truck that is traveling west. So we have 2 different directions if we were to draw this out, all right, we have a blue truck. This is a bad truck. It's a really bad truck. Traveling east, which is on a compass to the right, 20 meters per second. And then we have a white one. You can't see white, so I'm going to make it orange. So an orange truck traveling west at 10 meters per second. So the total momentum is not just going to be the addition of them, but rather one has a positive momentum, one has a negative momentum, so we do have to take those into consideration. So our total momentum in this case, so total, it's still, right, 1 plus 2, but we're going to treat them as vectors. So writing this out, we have the mass, so the mass of this large one is 1,500. So the mass is 1,500 meters, or excuse me, kilograms, multiplied 20 meters per second. That's to the right. We're going to add to that the second momentum. So typically how we write that is the same thing, mass times velocity. So mass times velocity, but the velocity is going to be backwards, and so as we've done in the past, we are going to say that the velocity is negative 10 meters per second. So probably should add a negative sign up here. So negative 10 meters per second. So the total momentum then becomes, what's that, 30,000 minus 7,000. Or a total of 23,000 kilogram meters per second. And so that's that. So, goodbye. Sorry, I had to say goodbye. With that, so now let's move to the big one, conservation of momentum. This is, like I said, this is the big idea that we're going to be looking at. So if we remember from class, so whenever two objects collide, Newton's third law tells us that they exert an equal and opposite force. So let's say we have a blue square and an orange square, all right, traveling towards each other. That one should be a blue arrow. You get the idea. When they collide, what do we see? The blue one exerts a force on the orange one. So I'm going to call this force F. I'm going to erase these other ones. These are going to be confusing. And the orange one exerts on the blue one the same force, right? And they are in contact for the same amount of time. Just by virtue of, they're always touching each other at the same amount of time. So the impulse, right? Remember, impulse, force times time, is they're going to be the same, right? Same force, same time. We talked about this in class. So what that means, or let me rephrase, they're going to be the same, right? But remember, one is going to be a positive and one is going to be negative. Like on the homework assignment, the football and the kicker's foot. The football had a positive change. The kicker's foot had the same amount, but it was a negative change. And you will find that all the time. The impulse on this orange one, this orange block, we're going to say delta P, a change in momentum, impulse, is going to be equal and opposite of this impulse on the blue one. So the blue one will have a negative impulse change because it's being forced towards the left, right, which would be the negative direction. And the orange one here would have a positive change. So we have an equal and opposite change so the impulses are equal and opposite. If we look at the system, we see that the total momentum is unchanged. All right, so if we have, kind of redrawing this real quick, we said that the orange one had a positive delta P and the blue one had a negative delta P. If we treat this all as one system, the total change in momentum is 0, right? So the change in momentum total Well, what we have, just like the momentum of a system is the sum of all the parts. Well, the same thing with the change. The change is the sum of all the changes. So we have positive delta P and subtract negative delta P, right? Or add, we're going to add them together, one's negative. And if these two values are the same, which they will be, then the change in momentum is 0 for the system. So it's a little weird, right? So the blue one has a change, the orange one has a change, and both of those changes are not 0. But when we add the vectors, right, one of them is backwards, they're opposite directions. So when you add them together, the total momentum change is 0. And that is the essence of the law of conservation of momentum. In any collision that occurs, the equal and opposite forces mean equal and opposite impulses, and equal and opposite change in momentum, and so the total momentum of a system means unchanged. All right, and that's the law of conservation of momentum. It is a law that defines, or not necessarily defines, but it is applied anytime two objects are colliding. Momentum will always be conserved in those collisions, if there are no external forces. And for this first video, we're going to be looking at that, and we're going to be looking at no external force systems. Obviously, if two objects collide, but then you push on them while they're colliding or something along to that effect, then you're adding a force. There's an external force acting on them, and that's going to affect the total momentum. But if you're just looking at the force in between the two blocks, those are internal forces because the blocks are exerting them on each other, and it's part of the system itself. So there's a few ways to write this. As I said, momentum, the change in momentum is 0, so that's obviously the first way to write it of a system. Another way is the fact that the initial momentum will equal the final momentum. All right, I'm being a little lazy. I should be drawing my vectors here. Excuse me. So if we take the total momentum of a system initially, we can equate it to the total momentum of the system afterwards because the change will be 0. We're going to apply this real quick in this video, or in this slide. Last example. So let's say we have two carts traveling on a physics track. It's like the tracks that we have in class. One of them is traveling to the right, and one of them is traveling to the left. All right, and I've given you their respective masses. So we have one cart traveling to the right at a speed of 10. Well, that's not right at all. Excuse me. At a speed of 0.4. Get out of here. 0.4. And then we have another cart traveling to the left, and this one's a bigger cart. Traveling to the left at 0.4. So whenever they collide, based on what happens after they, the momentum they have after they collide will be the same as the total momentum before they collide. All right, that's what it means. So initially, right now, there's a certain amount of momentum. Let's find the initial total momentum. I'm trying to write legibly here. So this is what, P1 plus P2, right? And we're looking at the vectors. So the first one, P1, we have moving to the right, so 500 grams, so the mass is 0.5 kilograms times the velocity, 0.4 meters per second. All right, plus, I got the blue one now, plus the second cart, which has a mass of 1.0 and a speed of, or a velocity of, negative 0.4 meters per second, because it is traveling to the left. And so the total momentum will be, so we have what, 0.02, excuse me, 0.2, I lied, 0.2, minus 0.4. So the total momentum is 0.2 minus 0.4, or negative 0.2 kilogram meters per second. It is negative, which kind of makes sense, right? The red one here that I've drawn is moving to the right, but the blue one is moving at the same speed, but it has twice as much mass. So there's actually more momentum moving to the left. So the total momentum initially is negative because it is pointed in the leftward direction. So let's say that afterwards we measure, let's say that they bounce off and we measure a final speed. Well, you know what, we're going to go ahead and leave it at that for now. Whenever we come to class, we are going to do this demonstration of this in class, and we can look at it more in depth. Then looks a little bit longer than I wanted it to be already. So we can say that after they collide, the final momentum will be also negative 0.2 kilogram meters per second, and we will explore in class in greater detail what we can do with that information. So that does it for this video. I will see y'all next week. Goodbye.